Hello, my name is Christopher Sacchi, and this project is regarding the evaluation of the Expedited Internet Bypass Protocol, otherwise known as EIBP, which is a new intra-AS communications protocol. The agenda for this presentation is as follows. We'll start with an introduction to the topic, describe the prior work done, explain the methodology, indicate the experiments and results, show a demonstration of the final project, and conclude with a conclusion and future work section. As a high-level overview of the project, the Expedited Internet Bypass Protocol was evaluated in an emulation. This was implemented using a software package called Mininet and was benchmarked against the Open Shortest Path First Protocol, otherwise known as OSPF. It focused on performance, scalability, and operational efficiency. The motivation for this project is that there are some limitations of traditional protocols such as OSPF. These include slow convergence, limited scalability, and a high configuration overhead. The improvements that OSPF EIBP has over this is a faster convergence time, better scalability across network sizes, an IP-agnostic design with a custom addressing scheme and minimal overhead, meaning that EIBP does not use IP internally. It can use it for backwards compatibility between access routers and hosts, and it doesn't have to though. And then finally, there's less manual configuration because EIBP only requires the core routers to be set with labels and the access routers, IP addresses, if any. Whereas with OSPF would require every interface to have an IP address configured. So the scope of work here is that the existing EIBP code is being adapted for emulation purposes in Mininet. The topology is being automated using a markup language called GraphML, or Graph Markup Language. Scalability testing is being done in a progressive fashion from a small to medium to larger network size. Performance is being compared with OSPF, which will set the foundation for a detailed methodology, results, and analysis. So for prior work, for the existing intra-AS protocols that exist, one of the most common is OSPF, which is widely used for intra-AS or intra-autonomous system routing. It is often enhanced with bidirectional forwarding detection, or BFD, for faster failure detection. Other protocols that are in use include Enhanced Interior Gateway Routing Protocol, or EIGRP, and Intermediate System to Intermediate System, or ISIS. Some core issues with OSPF, though, however, include limited scalability, slow convergence under failures, a high control plane overhead, a large blast radius with network-wide updates on topology changes, which means that a lot of systems have to update at this, like link state advertisements have to be sent and flooded. So not only does this have to cause a lot of traffic, but it also causes a high computation cost to get the routing calculated, and packet loss will persist despite fast reroute mechanisms. So OSPF operates by a hierarchical design, with the backbone being area 0, with multiple optional areas being available that all have to connect to area 0, allowing for effective network segmentation and administration. Routers form adjacencies and exchange LSAs, or link state advertisements, and build a link state database, or LSDB. Path computation is done using the Dijkstra tree algorithm for routing decisions, and failure handling is generally triggered by missed hello intervals requiring read computation and state updates. The negative impact on scalability, is the increased cost of computation, a higher control plane traffic, and stabilization is slower in larger networks. The motivation for EIBP is that there's a gap between the modern hardware capabilities and the legacy protocol design, where the modern hardware is very capable, but the protocols are not using them as efficiently as possible. So EIBP is designed from the ground up to integrate the control and data plane without depending on IP. And unlike OSPF and IP, where the control plane for OSPF and the IP plane for data, EIBP does these all at once. It uses virtual identifiers, or VIDs, for structured routing. It supports core distribution and access layer separation. The expected improvements over the OSPF, regardless if BFD is enabled or not, is a faster convergence, a lower overhead, smaller blast radius with localized updates, lower packet loss during failures, improved scalability and efficiency in these dynamic data center environments. So, the high-level overview for the methodology is that the implementation and evaluation of EIBP is done using Mininet. It is possible to do this with the physical systems, but this is expensive and time consuming. So therefore, it's easier to emulate this. Another emulation system package is Fabric Testbed, which is a very useful one. Fabric is much more limited in scalability, but has very realistic timing, whereas MiniNet is more scalable, but has less realistic timing. Therefore, both are used separately to test EIBP against protocols like OSPF to get a more accurate picture. The goal is for scalable testing and comparative analysis with OSPF. So for the experimental environment, the virtual machine or VM is set up in RLIS, or the Remote Laboratory Emulation System, the RIT's VMware cloud system for virtual machines over the web browser, and using Ubuntu Linux 22.04 as a standard version that was stable, that supports these technologies that will be shown further. These include the MiniNet emulation system and FR routing for OSPF. FR routing is an open source package that allows for network. Allows for network protocols that are all implemented in it that can be used as needed. And the repository for EIBP MiniNet is set up as such, is cloned, and then the logs directory is created inside to allow for debugging. And this is not only a lot needed for functionality, but it's also needed to be able to see what's going on and know that it's working properly for debugging purposes. MiniNet allows for the large-scale emulation on a local system via something called Linux namespaces. So the network topology design is within a 3-tier architecture with core routers, distribution routers, and access routers. This is a key concept in EIBP, as it's like the way it works, and it reflects a realistic enterprise structure which is supporting scalability. So EIBP was originally written for Fabric Testbed, another emulation system mentioned previously, so that it can run in MiniNet, and this was some low-level C code. Key changes here were a namespace-compatible interface handling, indexing from 0 instead of 1. Now, before I get into the indexing, the namespace compatible is important because it was, let's say, on Fabric, you would be using ETH1. If the same address on let's say A1 is an access router one would be A1-ETH1. So therefore, it was not able to address the specific number to get the labels for the EIBP. Therefore, there had to be some updates in the C code to allow for this. Interface indexing from, as I said before, interfaces in MiniNet start at 0 instead of 1. So that was reset. A lot of loops had to be modified to get this to work. This global struct declarations had to be set with an extern. This is a low-level C concept where when the C toolchain was updated for this more recent, relatively more recent Linux system, the C compiler would not complain about this in the previous iteration, but with this it did. So these updates had to be made for it to successfully compile for the convention change for that. And then buffer overflows happen because of the namespace compatible interface handling, and this is because it would assume 5 bytes, which was each, let's say ETH1, and then a 0 character, which is a total of 5 bytes. So therefore, it would be prevented by using a larger size, because if you were using an access router, let's say ETH0, A1 ETH0, that would be more than 5 bytes. Therefore, various arbitrary sizes were tried and they worked, but what was ultimately decided was something called IFNAM-SIZ, which is a predefined maximum Linux interface size, and that is a total of 16 bytes, and that therefore allows for the very maximum Linux would support. Finally, a makefile was introduced for build automation, which will just automatically run the GCC compilation code, and also the clean part of it removes the code binary file in case it needs to be removed for updates. And then finally, as a key note for these key changes, It is important to note that the first two of these 5 changes are relevant only really to Mininet, but the remaining 3 are relevant to all of, regardless of what's used. So this can be beneficial for everything. So for the initial topology, this is a very simple one with 5 routers. And this is the core router. These are the distribution routers. These are the access routers. These are the hosts connected to the access routers. And this is a software package that came with Mininet called MiniEdit, and it's a graphical user interface for the first topology. The adjustments here is that that this is a nice proof of concept, but to get it to work, it had to be 2 things had to be modified for Python 2 to Python 3 compatibility. IP forwarding was disabled because eIVP is IP agnostic. It would add extra traffic to here. IPs were assigned to hosts and access routers, and logging and startup delays were added so that debugging can be done to make sure things work, and delays were done to make sure the network was stabilized. Even though this looks simple, it's actually easier in general programming to just design something like this by text. So not only is this this isn't scalable, both because of its nature of how it exports, but also the way that you do this. So this is limited by being static and not scalable. So the graph markup language or GraphML based automation solves this problem for larger topologies by having something that develops a dynamic topology generation in GraphML. The Python script that's been based on another Python script that does GraphML parsing not only parses it, but it builds a topology based on it in Mininet, configuring the nodes and IPs, disabling the forwarding for eIVP, and adding logging for debugging purposes and the delays for network stabilization. Now this has much more benefits, being scalable, repeatable, and manual effort is reduced. So as an example, you can run this as root. You have to run this as root. Shown as sudo to run as root. GraphML topo pi, which is the eIVP GraphML script, and then this is eIVP.graphml, which is the 8 router topology. And this is with 2 core, 3 distribution, 3 access, and then 3 hosts, each of the hosts connected to one of the access routers. Post launch should be able to allow for stabilization time, and connectivity should be validated using pings. This design constraints and scaling. So for design constraints, this is how each of these routers is named. So for core, distribution, access, and hosts, each of these names is like capital C is core, so on. And basically, it starts with 1 and then it goes forward 2. So this is just the same pattern. It doesn't have to be these many. This is just reflecting the 8 router topology. Their requirement is that host links have to be declared first, so that it's guaranteed that the access routers are connected to ETH0 for the host, each of them. And the other thing to note is that because of the undirected nature of GraphML, you only have to say, let's say a connection is made between C1 and C2. It'll also automatically be made between C2 and C1, so you don't have to do you just connect one way. That's it. The topologies that were tested include an 8 router, 13 router, and 23 router topology. So here is the 8 router topology. So you got the 2 core, 3 distribution, 3 access, 3 hosts. This one's the 13 router. You got 3 core, looks like 5 distribution, 5 access, and 5 hosts in each of the accesses that says. And then this is much larger 23 router after the 8 and 13. So this one has a lot of, looks like 3 core, then there's 5 of these and 10, so 10 distribution and 10 access. So, and then there's all these hosts too, and these are all the ones. So for OSPF, to integrate this, we had to have a separate GraphML script for OSPF, running as root sudo OSPF GraphML topology pi, eIVP GraphML. So this is running the 8 router topology, featuring an automated IP assignment. So this was an advantage over manual OSPF configuration like you normally have to do, set up via the FR routing package, and logging is done for debugging, should be there for making sure it works. And this enables direct comparison with eIVP under pretty much identical conditions. So the exact same the exact same computer, the exact same topologies. It just kind of allows for that so that can be done. So to make sure that we can validate and test, the network has to be stabilized before testing. To verify connectivity, host-to-host ping tests are done, and this is successful across 8, 13, and 23 router topologies. So the contributions from this are that eIBP was ported from Fabric to Mininet. GraphML is used to create the automation framework to allow for this to be automated. OSPF was implemented with the FR routing, which is the package that contains all those various software packages of network protocols. Builds are automated with a makefile. Multi-topology connectivity is done, and scalability was successfully tested. So for the experiment, though, eIBP and OSPF were evaluated, and the execution of this was automated using Python scripts and topologies that are defined in these files. Emulation was performed in Mininet. So as said before, that there was 8, 13, and 23 router topology. The goal is to assess that this functions and can scale. To validate this, connectivity tests were done in each topology, verifying that end-to-end communication works because of pings, correct protocol operation, and networks to make sure the network is stable after initialization. The results of this is that the protocols function, and all of them test cases completed successfully. Both of these protocols operate, eIBP and OSPF operated correctly in Mininet. They maintained full connectivity in the network, and they confirmed that this was successfully ported from Fabric testbed. The scalability results is that eIBP remained stable as the topology scaled and successfully operated up to 23 routers from 8 to 13 to 23, demonstrating robustness in larger networks. Viability, it was viable for scenarios of scalable deployment. Some of the key takeaways here is that automation with the GraphML, Python, and Mininet enabled consistent, repeatable testing. Both protocols validated that they both functioned. eIBP showed that it can really scale, and the foundation here is established for further performance comparison, for example, convergence and overhead. Here is a demonstration of the protocol. One second. Oh, here we go. All right, so here is the function of the right here. Hold on a second. Here we go. Okay. So here is the demonstration. So, sorry. So the demonstration shows that eIBP works in the. This is the 8 router topology, and this is running with. This is running, showing that each of these. Basically, there's 20 seconds in between. When it waits in between. When it waits at the end, after the access routers, it's waiting 2 minutes, but this has been sped up to 5. So this basically just will take a little moment, but yeah, it'll go back on. And let's see, so yeah, anyway, so access router 1, 2, 3. These are each of these. So yeah, there's 4 pings on each. So that's the first one. This is the second one, and it's taking a second to. So this is the 13 router topology. It says 13 node. They should really say 13 router, but regardless, it's running 2. This has been set to fit within 5 minutes, so it's pinging successfully here. One last one is the 33 node. This one is correct because it's 23 routers and 10 hosts, so this one therefore is 33 node. And as said before, in between those, when it says assignment and this is waiting, that's in real time, that's 20 seconds. And then there's 10 of these. So this will run, and I'm just waiting a second for that. So this is there's 10, so it's pinging successfully 4 times, and then finally OSPF runs. This is the OSPF version, so right after it finishes, pretty soon after really, it's just a 2-minute mark really, and it'll just run this and then load in EIBP. So yeah, that's that. This one's running the, not EIBP, I mean it's named that, but it's running the, as it said before, this is the 8 router topology. Okay, it's running. I'm exiting. So this one is the 13 router topology, and it'll take a second. And this is the last one. This one's the 33 node or 23 router topology. And in a moment it'll work. Okay, and the pings work. And that's it. So it takes a little longer to exit with all the different things, but there it is. Overall, it looked good. So back to going past the test demonstration. Let's see, I just want to... So the conclusions is that we demonstrated the performance improvements that EIBP has over OSPF, which was evaluated using Mininet across multiple topologies with 8 router, 13, and 23, confirming scalability and stable operation of EIBP, and the results are documented in this presentation and the report. For future work, can extend the evaluation beyond what it has with additional metrics such as convergence time, control overhead, blast radius, and packet loss, comparing OSPF with and without BFD, validating performance on physical hardware with more realistic deployment conditions, improve resource optimization. So some of the final takeaways include that EIBP shows strong potential as a next-generation intra-AS protocol, some of the key advantages being minimal configuration, IP-agnostic design, as I said before, explained, fast convergence, low overhead and reduced blast radius, and high scalability. Therefore, it is suitable for data center networks of varying sizes.